In this video, I'll show you how to solve the ALEKS problem called using relative effusion rates to find an unknown molar mass. To help you solve this problem, you are going to want to have a periodic table handy, one that has molecular weights or atomic weights on it. And so for this problem, we've got two different gases. ALEKS is giving us information about the identity of one of the gases. For my problem, it's an O2 gas. And then we also have an unknown gas. Now, I want you to pay a lot of attention, look at your problem really carefully right now, because there are two different versions of this ALEKS problem. One version says that you're dealing with a homonuclear diatomic molecule. That's what I have. Another version of this problem tells you that you have, it says that it's a gas made up of atoms. Doesn't say that it's homonuclear diatomic, it just says it's a gas made up of atoms. Now the general process for solving the problem is going to be the same, but at the very end of the problem, the very end, which of course is the most important part, we're going to take a slightly different route for the solution based on whether you have homonuclear diatomic or just atoms. So make sure you are paying attention to that once we get towards the end of the problem. Okay, so this is giving us information about the relative effusion rates. Effusion is just the process of this gas escaping through a pinhole. That's just the effusion process. And it tells us that for this unknown gas, whatever it is, the unknown gas rate of effusion is 0.918 times faster than our known gas. So for me, that's oxygen. This is the equation that we're going to use to solve this problem. In this equation, R1 and R2 represent the rates of effusion of these two gases. I'm going to say that let's call our unknown gas rate of effusion, we're going to call that R1. That's the rate of effusion for the unknown gas. Notice that it does not tell us what the rate of effusion is for the other gas. It doesn't tell me what the rate of effusion is for oxygen, and that's okay. And because it's not actually telling me what the rate of effusion is for my unknown, it's just telling me that it is 0.918 times faster than oxygen. So we don't know the actual numbers of R, we just know the relative or the ratio of R. So R1, we're going to call that 0.918, that's our unknown, and our R2 rate of effusion is just going to be 1. Now if that really super confuses you or just really kind of blows your mind, that it's kind of a math trick that we're doing there, I'm just going to say, I'm going to ask you just to kind of let it go. Trust me. R1 is whatever number that is that ALEKS is giving you, and the value of R2 is just going to be 1. And again, these are not the actual rates of effusion. These are just the relative values of R1, the ratio of R1 to R2. Now next we have a square root of A2 over A1. Notice that the numbers are now the other direction. We have 1 over 2, and on the other side we have 2 over 1. These numbers represent the atomic mass or the molar mass of the gases. So A2 represents the molar mass of gas number 2, and A1 represents the molar mass of gas number 1. I said that R1 is my unknown, and that means that A1 in this equation, I've got to keep my subscripts consistent. That's going to be my molar mass of my unknown. And so that means that A2 is going to be the molar mass of the gas that has been provided to me in the problem, which is O2. And this is where the periodic table is going to come in handy to get the molar mass of O2. We're going to just take a look at the periodic table. We're going to find oxygen. It has an atomic mass of 16. We've got an O2 molecule. That means that the atomic or the molar mass is going to be 2 times 16, which is 32 grams per mole. And so we're going to plug that into the equation right here. 32, I'm going to leave off the units, grams per mole, because A2 has units of grams per mole and A1 also has units of grams per mole, and they're going to cancel each other out. So 32 divided by my molar mass of my unknown. That's what ALEKS is asking us to solve for in this problem. That's the unknown variable. So the next thing that we have to do is just some tricky math to sort of solve for this unknown, which is at the bottom of a fraction inside a square root. But that's okay. We can handle the math. We're going to start by getting rid of the square root symbol. To do that, we're going to take this. We're going to square both sides of this equation. 0.918 squared is 0.842724, and that is equal to the square root, I got rid of the square root. That is equal to 32 over our unknown A1. Now what I'm going to do is multiply, actually I'm going to use the cross multiplication rule. I'll go ahead and bring that one back. And we're going to say that the numerator times the denominator is equal to the numerator times the denominator. And so that's going to give me 0.842724 times A1, my unknown, is equal to 32. And then the last thing that I need to do is divide both sides of this equation by 0.842724, and that will cancel that term out. On the left-hand side, 0.842724. Cross that off. 32 divided by that is 37.97. That is my atomic mass, or my molar mass, of A1. Now here's where the problem is going to be different based on whether you are looking or dealing with an atom versus a homonuclear diatomic molecule. If you have the version of the problem where it just says you have a gas of atoms, this is the atomic mass of that unknown gas. And what you're going to do now is go to the periodic table and you are going to find the atom that has an atomic mass of approximately 38. And we're not going to be able to find that on the periodic table because there isn't one. That's not the problem isn't asking me to do that. But if you had been given the problem where you were solving for an atom, you should be able to come up with a number that is matching up really well with one of these atomic masses. If I had the version of the problem that said gas made up of atoms and I had calculated an atomic mass of 38, which doesn't match up with 35 and it also doesn't match up with 40, I would go back and check my math because that would be an indication to me that I had done something wrong. But if my mass that I calculated was 40, I would say, boom, there it is. My gas is argon. ALEKS is asking us to identify that gas, and that would be my answer. I do not have that problem, though. I have homonuclear diatomic. What exactly does that mean? Homo means same, nuclear. So this means that I have diatomic means two atoms. So I have two atoms that are the same in this molecule. This is the molecular weight of a molecule that is made up of two identical atoms. So what I'm going to need to do is divide this number by 2 to give me the mass of each individual atom. I'm getting 18.99 grams per mole. And again, that just kind of blew your mind as well. But this right here, for me, this is the mass of my molecule that is made up of two identical atoms. And in order for me to know what those atoms are, I need to divide this mass by 2 so that I can figure out the mass of each one atom that is in that particular molecule. Now, with that, I'm going to go to the periodic table and I'm going to look for the gas that has, or the atom that has a mass of approximately 19. And that is fluorine. Look at how good of a match that is. So my unknown gas, my unknown atom is fluorine. I have the fluorine atom, but again, I've got 2 of those in my molecule. So I have the F2 molecule, and the formula of the gas that I have is F2. ALEKS does not need you to write the state, doesn't want you to write the gas symbol in parentheses. This last little step right here is going to be the trickiest part of this problem, especially if you're dealing with the homonuclear diatomic. If you're dealing with the homonuclear diatomic, the value that you get of A1, you're going to need to divide it by 2 to get the individual atom so that you can identify that individual atom, but then also don't forget that there are 2 of them in the molecule, and that's what the answer is to the problem.